Yes, from this video onwards, I'll be talking about abstract algebra. I've been wondering if I should do it or not, but finally, someone from Tanzania requested for this, and finally, I think I have the opportunity to go ahead and do it once and for all. So, introduction to abstract algebra is what this video is about because we embark on this journey about abstract algebra and see how far we can go, trying to touch every aspect of abstract algebra. So, by way of introduction, our goal is to learn the basic language of abstract algebra, sets, operations, groups, subgroups, cyclic groups, permutations, homomorphisms, rings, and fields, right? So, I mean, you'll understand what this whole thing is about by the time as we progress in this particular video. So you can see already that the basic thing, the fundamental, the basic thing abstract algebra is based on is set theory, right? So from set theory, then we blow it up and then it becomes abstract algebra. So let's go gradually. What is abstract algebra now? What is abstract algebra? So, um, abstract algebra studies structures. It's basically about studying structures, like groups, rings, and fields defined by axioms. And that is why one of the first things we'll see about group theory is the idea of group axioms and some examples, as you're going to see in a video ahead of now, not maybe not the next one. So in this video and the next two, the focus is on some fundamentals of algebra, of abstract algebra. I mean, some mathematical foundations, that is. So instead of focusing on what the objects are, we focus on what rules the operation satisfy. So we have the objects, right? Then we focus on the rules they satisfy. Then the typical objects included in abstract algebra, typical objects in abstract algebra, I mean, include integers under addition, non-zero rationals under multiplication, symmetries of shapes under composition, and polynomials under addition and multiplication. So we are going to see all of this as we unpack the whole idea of abstract algebra. So we go on to uh, sets and binary operations as one of the as the basic idea upon which abstract algebra is based. So I mean, the set and binary operations are the basic ideas upon which abstract algebra is based. So a binary operation on a set S. So imagine you have a given set S. So a binary operation on that set S is a function such that when you operate, when you carry out the function on two elements in S, the answer you end up getting also belongs to the same S, like that. So this means that for any A and B belonging to a set S, the result of A star B, A asterisk B, will also be in S. And this property is called the closure properties. So the idea of closure is that, so if you pick any two elements of a particular set, and you carry out a particular operation on the on the uh on the element, the answer you get must also belong to the same set from which you took those two elements, and that is what is called the closure property. So I mean, that's one property among so many. So any operation that does not obey the closure property cannot be said to, I mean, there are some things we can say about it cannot be said to be closed, right? And then it also has some other implications as we move on to other objects in abstract algebra. So we have our first worked example here. Imagine you have the set S, which contains elements 1, 2, 3, and you define a property A star B. So a binary operation A star B, which is A plus B. So that means this asterisk is an addition operation. So we want to now check the closure. So if you do anything if you pick any two elements of this set and you carry out addition on it, and you get the result you get is also here, then you can say that the operation is closed. But if not, the operation is not closed. Imagine if you pick 1 plus 2, you get 3. Okay. But we can't conclude with that. As far as there's any two you pick that doesn't give you the same result, then it's not closed. So 1 plus 2 is 3, that's fine. 1 plus 3 is 4. That's a problem already. 2 plus 3 is 5. That's a problem already. So to check for closure, now you can pick up, so try all the possible additions you can do. So if all the results you get are also part of this set, then you can say that operation is closed. Otherwise, it's not closed. So if you do two by once you get a particular one situation, you don't need more than one. Once you get one situation where the closure property is not obeyed, then you don't even have to you just have to quit trying, right? So you're looking for one situation where that rule of picking two elements and carrying out the operation and the result, not being in the same set you pick the two elements from. So once you have a situation like that, then the closure is not obeyed. So you have 2 star 3, which is 2 plus 3, and that's 5. But you see, 5 does not belong to the set S. So in that case now, we say the operation star is not a binary operation on the set S, like that. Okay? So let's look at some common properties of operations. For an operation star on S, we checked associativity, which is A star B star C. And that means that whether you do A star B first or you do B star C first, as far as A, B, and C are all involved. So whatever you do first doesn't matter. You get the same result. We are going to see all of these things as we move on. Then there's commutativity, A star B, B star A. Okay, I mean, a very simple example I can give here is that addition is closed under addition is associative rather under in the set of integers. We are going to see all of these things later. So if you have 2 plus 3 plus 5, for instance, 2 plus 3 plus 4 rather, 2 plus 3 is 5, 5 plus 4 is 9, or you have 2 plus 3 plus 4. So you can do 3 plus 4 for 7, then 2 plus 7 is 9. So that way, addition is associative over on the set of integers because the answer you get is also integer. Then for commutativity, A star B is equal to B star A. Addition is commutative, multiplication is commutative. Like I think that's over the whole real number set for sure. So for instance, if you have 2 plus 3 is equal to 3 plus 2. 2 times 3 is equal to 3 times 2. That's the idea of commutativity. Then you have identity elements. So for identity element, there existed a particular E with E star A such that A star E is equal to A. So I mean a very good example of this is of course addition and multiplication. So imagine there's an identity under addition, for instance. Okay, I guess I should begin to write here. So we're talking about identity element, right? So that at least I can, we know it's abstract, but at least let's try to get the point home as much as possible. So we say that for identity, right? For identity element, there's a particular E such that A star E is equal to E star A, and that is always equal to that A. So, and that is equal to E star A. So, for instance, under addition now, you have, imagine, under addition, can you think of a particular number that if you pick a number 7 and you add that number to it, or you add the number, okay, I've given away the answer, but it's okay. Or you add or you say the number plus 7, you always get 7. Can you think of a number like that? Of course. Under addition, the number is 0. Number is 0. And that is why 0 is the identity for is the so we say 0 is the additive identity. Okay, so for addition, 0 is an identity because anything you add 0 to, anything you add to 0 is always it always gives you whatever you add it to or whatever you add to it. So that's the idea of identity. Then there's also the idea of inverse, that for each A there existed A inverse with A times A inverse equals A inverse times A equals E. Now that's another idea again. Okay, I think we also have the same thing for multiplication, right? So for multiplication, imagine, can you think of a number that if you multiply 7 by that number, or you multiply the number by 7, you always get 7. For multiplication, the answer is always 1. So in this case, now 1 is always the multiplicative identity. Multiplicative identity. Okay? So that's that. And then we talked about the idea of inverse, right? So talking about inverse, we're saying that, there's a particular A inverse such that A operation A inverse is equal to A inverse operation A, and that is always equal to the identity element. Okay, I think that's what we have for this identity, for this inverse inverse now. So the inverse is such that when you operate A by its inverse, you always get the identity element. Now we can of course do the same thinking for both addition and multiplication. Can you think of a number that, okay, let's go. Say for addition, for instance, can you think of a number such that if you have, okay, let's still go with the 7. So you have 7 plus something plus the inverse of 7, and that is always equal to that inverse plus 7, and that will always give you 0. Okay, so because we have identified 0 as the additive inverse, like that. So what will you add to 7 and what will you add 7 to? That will always give you 0. Now, of course, that is going to be minus 7. So 7 minus 7 is 0, minus 7. So here now, as far as 7 is concerned, under addition, minus 7 is the additive inverse. Minus 7 is the additive inverse. So generally speaking, for any number, minus of that number is the opposite sign. So, I mean, still talking about additive inverse, right? We could actually say that, so if you have minus 3, what will you add to minus 3? Or what will you add minus 3 to? That will always give you 0. That is simply plus 3. That's simply the positive 3. That's the idea under addition. So, talking about multiplication now. So, under multiplication. Okay, I mean, I can just use the sign. So for multiplication, imagine what can you multiply 7 by, or what can you multiply by 7? That will always give you the multiplicative identity, which is 1, right? So easily, that will be the inverse, the 1 over 7, right? That will be the reciprocal of 7. That's 1 over 7, or well, I mean 1 over 7. So if you do 1 over 7, you get 1 like that, right? So in this case now you say that this 1 over 7 is the multiplicative inverse of 7. So this is multiplicative inverse of 7. Okay? So on the other hand, if you have like a fraction, so if you have 3 over 4, what will you multiply by 3 over 4? Or what will you multiply 3 over 4 by? That will always give you 1. Okay, so that will automatically be the reciprocal of 3 over 4, which is 4 over 3. So 4 cancels, 3 cancels. So 4 over 3, 4 cancels, 3 cancels. So we have 1 like that. So that's the idea of multiplicative inverse, and that's like an example. So it's not just always about plus addition and multiplication. So watch out for that. Okay, now you can see after I've been talking about addition and multiplication, because if you introduce division and subtraction, commutatively, for instance, will not work, because 2 minus 3 is not 3 minus 2, right? So all that. So we focused on addition and multiplication. So imagine this example on Z is the set of integers. So define A star B equals A minus B. For commutativity will fail because 5 minus 2 is 3, but 2 minus 5 is minus 3. So the answers are different, though it's all about the sign, but they are not equal. Then associativity will also fail for subtraction, because 5 minus 2 minus 1 is 5 minus 2, that is 3. 3 minus 1, that is 2. Whereas on the other hand, if you have 5 minus 2 minus 1, so if you do 2 minus 1 first, that is 1. 5 minus 1 is 4. So you see, associativity fails, commutativity fails under subtraction. So we can say that subtraction is not commutative and it is not associative on the set of integers. So subtraction was neither commutative nor associative like that. So don't forget, this is still foundation for the for abstract algebra proper. So let's talk about the definition of a group. So like we already saw that abstract algebra is all about studying some structures, some algebraic structures like sets, groups, rings, fields, and all of that. So let's go. So a group G, comma, star, comma, dot. Now, you have to pay attention to this. So this group now is G, and you have a particular dot. So the group now consists of a set. So this G is a set with a binary operation. So this dot is a binary operation. It could be addition, multiplication, whatever you define at any point in time. So this group now, so you write a group with, so you see, set normally, right? So if you have a set and a binary operation put together, it becomes a group.
So a group G, comma dot is a set G with binary operation dot such that closure is obeyed. That is, A, B belong to G. That is, if you say A dot B, it belongs to G for all A and B belonging to G also. So if you take A and B from G and you carry out this binary operation on A and B, the result you get, which is AB, also belongs to G. We talked about that idea of closure before. And then there's associativity. That is, if you say A dot B dot C, it's the same thing as A dot B dot C. That's if you do AB first. So if you do AB.C or A.BC, it's associative. All right. Then there's also the identity thing we talked about. So there exists the identity element E, which belongs to G, with E A equal to AE equals A, basically. So that is also the idea of identity. Then we have inverses. Now, for each A belonging to G, there exists A inverse belonging to G with AA inverse equals A inverse A, which is equal to the identity element. So if also AB is equal to BA for A and for all AB belonging to G, then the group is said to be abelian, right? So you see that for a group to actually be a group, it consists of a set G and a binary operation, and together they obey the closure, associativity, identity, and inverse properties. But then there's this extra layer, which is, I mean, this does not necessarily need no group, every group does not have to have this. So that's why this point is just an extra. So once you have a group and a binary operation that obey this for it is closed, it is associative, it has an identity element, and it has an inverse element, then you can say that is a group. But if the group is commutative, that is, if AB is equal to BA for all A and B belonging to G, then you say you have an abelian group. You say the group is abelian, and that is named after N.H. Abel, one of the pioneering people in mathematics. Okay, now let's look at this example where the set of integers with under addition is a group, right? So these all positive, all integers, whether positive or not, and positives, and you have plus sign. So this is a group. Now this is a group Z with this sign. So in Z plus now, closure would hold always because A plus B belong to Z. That is, take any two integers, add them together, the result you get will also be an integer. That's established for sure. So then associativity also holds. Like, take any three integers and add the first two before you add it to the third one, or keep the first one, add the last two before you now add it to the first one. You get the same result. That is associativity. Then you have identity. So for addition, I already showed you that for addition, the multiplicative identity, I mean the additive identity is actually zero. That is, add zero to anything or add anything to zero, you always get that thing. Not you get that thing you add it to, or that thing you add to zero, right? Then there's also the idea of inverse of A. So the inverse of A would be minus A, since A plus minus A will give you the identity like that. I showed you that on the worksheet. So Z, comma, so the group the group consisting of the set of all integers and the binary operation of addition is an abelian group. It's also an abelian. It's a group, first of all. So we have established with it that it's a group. It is also abelian, meaning that if A plus B is always equal to B plus A in the set of all integers. Okay. So you have to be sure, so before you can conclude this for any particular set, you need to know the properties of the set. You need to know how the set behaves and how the operation itself behaves, right? So can we say that I mean, this is a non-example now, that the set of all integers with this binary operation of multiplication is not a group. Okay, let's see. So in this now, we have an identity element one for sure, but many elements have no inverses in Z. For instance, this is a set of all integers. So if I say 2 divided by 3, the answer is 2 over 3. In fact, 3 over 2 is 1.5, and 1.5 is not an integer. 3 over 2, 2 over 3 is 2 over 3 is 0.66666. So it is a recurring decimal. So you can see it is not an integer. So because of things like that, because there's no, first of all, uh, we have the idea. Okay, there's no closure even. Yeah, there's necessarily no the closure is obeyed, yes, because 2 times 3 is 3 times 2 always. There's closure, there's identity element 1, but there is no inverse in that same set. So many elements have no inverses in Z. So example, the inverse of 2 would need to be 1 over 2. But 1 over 2 is not an integer. It doesn't belong to the set of integers. So Z and multiplication is not a group. So, so you can see Z under multiplication is not a group. So, but what I explained here, of course, don't forget this is not group I explained here. I was just talking about the concept of inverse identity and inverse generally. But for group now, all these conditions have to hold before you can say that a particular set and its binary operation form a group. So let's go on to talk about modular arithmetic for Z sub n. Of course, don't forget Z again is was talking about integers, right? So Z sub n. So if we define Z sub n to be 0, 1, 2, all the way up to n minus 1. So if you have Z5, for instance, it means that to be, Z5 will be 0, 1, 2, 3, 4, right? You stop at 4, that's 5 minus 1 with addition mod n, okay? So in this case now, so we're talking about this this for modular arithmetic, we have this Zn with additional mode n, then Zn and plus is a finite abelian group. So, and we have an example of that right here. Okay, so imagine you want to compute Z7. So, you want to compute in Z7. In Z7, right? 5 plus 6 is equal to 4. Okay, yeah, look at this now. First of all, when we talk about Z7, Z7 means you have the collection of 0, 1, 2, 3, 4, 5, 6. And now we have Z7, we have a group Z7 under modular addition. Okay, that's addition mode 7. Okay, what that means is that you don't ever get any number above 7. Okay, what did I do here? This should be 5, right? Should be 5. Okay, so mod 7, that's what that is about. So anything that is bigger than 7, you have to divide by 7 and take the remainder alone. So in Z7, right, we have 5 plus 6 to be 11 normally, but then 11 divided by 7, that's 1, remainder 4. So that remainder now is what you have here. So 5 plus 6 in Z7 will be 4. And it is contained in this group, as you can see right here. Okay. Then the additive inverse of 3 is 4, because 3 plus 4 will give you 0. Okay. 3 plus 4 is equal to, 3 plus 4 is similar to 0 under modular addition like this. So every element has an additive inverse mod 7. So in this case now, so this is a very good example of a group under modular arithmetic. Okay, let me go back and explain what I mean here. So we are trying to see if Z7 with modular addition is actually a group. So first of all, we have to be sure that if you pick any two elements, okay, if you pick any two elements, so you have to run through all the elements possibly. So you have 0 plus 1, that's 1, which is here already. 0 plus 2, that's 3, that's there already. 0 plus 4, that's 4. 0. Okay, 0 plus anything is fine. So go to 1. 1 plus 2 is 3, that's here. 1 plus 3 is 4, that's here. 1 plus 4 is 5, that's here. 1 plus 5 is 6, that's here. But guess what? 1 plus 6 is 7. And since we are working in mode 7, so it's just 7 and 7, that's 1, remainder 0. So this 0 is what you take. So the 0 is here, right? So that's for 1. For 2 now, you have for 2, you have 2 plus 1. 2 plus 0 is 2. 2 plus 1 is 3. 2 plus 3 is 5. That's here. All right. 2 plus 3 is 5. 2 plus 4 is 6. 2 plus 5 is 7. So, and 7, because 7 mod 7 is 0, like that. Then 2 plus 5 is 7. Okay, 2 plus 6 is 8. Now, 8 divided by 7, because we are working in mod 7. So 7 and 8, 1, remainder 1. So this 1 is what you pick. The 1 is here. Okay, so if you go 3 plus 4, 7, that is simply 0. 3 plus 5 is 8. That is 1. 3 plus 6 is 9. So you have 9. 7 and 9. That is 1, remainder 2. So that 2 is what you pick here. So it's there. So what else? Then you can go 4 plus 5, 9. Okay, we know 9 is 2. 4 plus 6 is 10. 10 divided by 7, that's 1 remainder 3. So this remainder is what you pick. So the 3 is here. Then you can also go for 5 plus 6. So the biggest you can have is that 5 plus 6, which is 11. In mod 7, 11 mod 7, like we've been doing, is actually, so you have 11, you divide by 7. That's 1 remainder 4. So this 4 is what you pick. So the 4 is here. So you see that all of them, so you can see that, first of all, Z7 is closed like that. So Z7 is closed, first of all. And then I am sure it is also, it is what else is there? It is associative. It is associative. So we've established closure based on what we have done now. And for associativity, I'm sure if you pick any three numbers, any three, the worst, let's even pick the big three. 4 plus 5 is 9. All right. 9 plus 6. 4 plus 5 is 9. 9 plus 6 is 15. So divided by 7. So 15 divided by 7, that's 1 remainder 1. So you still have that 1 here. So it is also associative. Okay. Then do we have an identity in this case now? So what can we are talking about addition now. So what can you add? Anything you pick. So you have, say you have 3. What can you add to 3? All right. Which will give you, or add 3 to, that will always give you, sorry, that will always give you 3. Okay, well, it is still 0. So pick any number. So you add 0 to it, add it to 0, you always get that number. So it has it has identity, clearly. So the identity remains 0 for addition, as usual for addition. And then the last thing is about inverse. Do we have inverse here? So let's check. So if you pick any number, say you pick 6. So imagine picking 6. So imagine, what will you add to 6? What will you add to 6? Or add 6 to, or add 6 to, sorry, or add 6 to, and you always get 0, okay, which is the inverse. So in this case, you have, that will be 1, right? That will be 1, because 6 plus 1 is 7. 7 divided by 7 is 1 remainder 0. Okay. So that's 6. So if you pick any number here, for 5, it will be, the inverse is 2. So the inverse of 6, like we found, is 1. The inverse of 5 is 2. Because if you add 5 to 2, or you add 2 to 5, it gives you 7. 7 divided by 7, that's 1 remainder 0. And that 0 is what you pick. So this will be 3, this will be 4, this will be 5, this will be 6. And of course, the inverse of 0 is 7, right? So it's more like you are now counting it backwards. Okay. The inverse of 0. Oh, we don't need the inverse of 0. It's not necessary because it's 0 already, right? We don't need to worry about that because it's already 0, so we don't have to care. So, but you see, for the other ones, you can take it for 1 to 6 from the back. And that is how it will be for other modular stuff like this, right? So, so we can then boldly say that that Z7 is, okay, better still, Z7 under modular addition is a group, like that. Okay. So, um, yeah, so every element has an additive inverse mode 7, like I just explained over there. Okay. So, yeah. So if I have another opportunity, I think I'll spell it out better. Right. So unit mod n and multiplicative inverses now. Not every non-zero element in Zn has a multiplicative inverse. Aha. So what we did before was about addition. So for multiplication, it's not always the same. So not every non-zero element in Zn has a multiplicative inverse. So the units are Zn star, which is equal to a belonging to Zn, and we get the great circle, the great common divisor of a and n, and that is 1. So this form a group under multiplication mod n, right? So under multiplication mode n, so if we have a belonging to Zn such that the great common divisor between a and the n itself is equal to 1, then this can then form a group under multiplication mode n, like that. So we have an example to buttress the idea. So we want to compute Z10x by checking the great circle distance between a and 10. So a and 10 is, if a and 10 is equal to 1. So a and 10 is 1 for a equals 1 to 9. So if you have
1, 1 for A equals 1 to 9, right? Um, so the units will now be 1379 because 1 and 10, only one is common. 2 and 10 will not work here. 2 won't work here. But then there is 3. 3 and 10 works because the greatest common divisor of 3 and 10 is 1. 4 and 10, you have two there and all that. 5 and 10, no. 7 and 10, yes. 6 and 10, no. 8 and 10, yes. 9 and 10, yes. So only thing that can divide both 9 and 10, the biggest number that can divide both 9 and 10 is 1, like that. So in this case now, the units are 1, 3, 7, and 9. Okay, so because we're talking about unit mod n and multiplicative inverses, so the inverse examples will now be, so what will you multiply by 7 that will make you get the inverse back? That is that is 3 times 7, that will give you 21. And so, and 21 divided by 7, 21, we are talking about mod 10. 21 divided by 10 is 2 remainder 1, and that one is what you pick in mod 10. So 3 inverse is simply 7 in Z10 inverse. Okay, well, let me really buttress this idea. All right. So pay attention basically to this, that not every non-zero element in Zn has a multiplicative inverse, but then we can have units defined by Zn star and all that. So let's go over to the worksheet page and deal with that decisively to drive home the point as much as possible. Okay, so we go here now. So we're talking about Z10 under multiplication. Okay, so you have Z10 under multiplication. So imagine Z10 mod. Okay, Z10 multiply mod 10, of course. So, of course, first of all, Z10 generally is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. We don't get to 10 because generally this should be 0, 1 to up to n minus 1. So that's Z10, first of all. But then, if you talk about, so for us to be able to get the unit mod n, right? So first of all, we check GCD. So GCD of a comma 10 equals 1. Which things meet this condition? So it means check. If you do GCD, the great common divisor between, uh, of course, if you pick 0 and 10, I mean, makes no sense. But if you pick GCD 1 and 10, yeah, that makes sense because this is 1. The GCD is 1. So if you have GCD of 2 and 10, okay, 2 and 10, the greatest common divisor is 2, okay, 2. But that doesn't work. So we are interested in this. Then if you have GCD between 3 and 10, that's greatest number that divides 3 and 10. So for 3 and 10, that's 1. That works. We need this. Then we imagine GCD for 4 and 10. So these are the possible A's now because you already know that is what Z10 is. So GCD of 4 and 10, of course, is 4. I mean, it's 2 rather. So we don't want that. Then you have GCD of 5 and 10. GCD of 5 and 10 is 5, so we don't want that too. Then you have GCD of 6 and 10. So the biggest number that divides 6 and 10 is 2, so we don't want that also. So imagine GCD of 7 and 10, that is 1. Okay, the biggest number that divides 7 and 10 is 1. So we want this. Okay, so take note. We had 1, we had 3. Now we have 7. But we keep going. GCD of 8 and 10. GCD of 8 and 10 is simply 2. All right, we don't want that. Then GCD of 9 and 10 is equal to 1. So that is needed, right? So at the end of the day, those are what we can call the unit mods. We don't go to 10 because 10 is not part of Z10, right? So with this now, we can then see that the unit mods, the units are those ones that satisfied that GCD thing. That's 1, 3, 5, and 7. I mean 1, 3, 5, 7. Sorry, 5 is not there, sorry. 1, 3, 7, and 9. Okay. These are the units. So now, um, so now we have, so this can then work, right, for ZNX. This is the only set that can work for that, right? Z10x, Z10x. So you have 1379. These are the units that work for that, right? So now the question is, would this now be like a group, right? First of all, we have the idea of closure, okay? Let's start with closure. If you pick any two numbers. Let's investigate closure. So pick any two numbers. What are the possibilities? You have 1 plus 3. 1 plus 3 is 4. Okay. 4 is not here. Okay. 4 is not here, right? So, okay, maybe that's not the deal here. I think we're just talking about, so these are just simply called units, not Z10x. Let me not mislabel it like that way. So not Z10x, but um, so just like what we saw the other time, right? Not every non-zero element in Zn has a multiplicative inverse, right? So for instance, if we pick 1, we are talking about multiplication, right? If we pick 1, okay, well, the multiplicative inverse of 1 is 1, so no wahala, no problem at all. Then if you pick 3, so what will you multiply by 3? Okay, or what will you multiply 3 by so that you can get 1? Okay, so um in the case of 3 now, either if you multiply 3 by 7 or 7 by 3, you get 21. But we are talking about mod 10. So 21 mod 10 will be something like 21 divided by 10. 10 in 21 is 2, remainder 1. So this 1 now is, you have it right here. So that's an inverse right there for you, as we can see over there. So here now we are not claiming that 1, 3, 7, and 9 is a group. No, that's not what we're saying. We're just calling it what it is: units mod n, and the possibility of having multiplicative inverses. And we already see not every non-zero element in Zn has a multiplicative inverse. So the units are, so Zn, that's given by the fact that all the A belonging to Zn such that the greatest circle distance of an is 1. So that is what, those are the units. So this now form a group under multiplication mod n. So this actually form a group under multiplication mod n. Okay. So we have that. So as you can see here, 3 times 7 is 21. In mod 10, you have 1. So 3 inverse is actually 7 in Z10x. Okay, so these together now, they form a group under multiplication mod 10, like that. Okay, so I was going to talk about all these inverses and everything. So at the end of the day, that 4 we had, right? I think we had a 4 here. Maybe I should have even continued, but we'll look at that better, because this is just introduction. We're still going to drill into these things deeply as we move on. So not a problem. So a subgroup H. So here we're talking about subgroups. A subgroup H. So there are groups and there are subgroups. So a subgroup H belonging to uh properly belonging to G, right? Is a subset H uh, which is a proper subset of G, that is itself a group under the same operation. So if G is a group under a given operation, so if H is its subgroup, then that H is also a group under the same operation. So a very useful test is this: a non-empty subset H, all right, a non-empty subset. Okay, this is long. Okay, a non-empty subset H, which is the proper subset of G, is which is an improper subset. Improper equality means improper. Sorry, I've been talking about this is like a proper subgroup. This is a proper subset. So sorry, improper group, because there's equality, they can actually be the same, like that. So a non-empty set H, which is an improper subset, which is a proper an improper subset, yeah, an improper subset of G is a subgroup if and only if for all A and B belonging to H, we have AB inverse also belonging to H. So if you want to say that uh H is a subgroup of G, right? Then if you pick a particular A and you do the operation with the inverse of B, whatever you get must also belong to H. So we have this point to drive that idea home. This example. So imagine 3Z is a subgroup of Z. Okay. Of course, we already know Z is every not every integer you can think about. So like
from negative to positive, including zero. So zero is also an integer, right? So say minus 10, minus 9, minus 8, minus 7, minus 6, minus 5, minus 4, minus 3, minus 2, minus 1, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on and so forth, to infinity to the right, infinity to the left. So that is what Z is, right? But 3Z is uh that's multiples of 3. So you have minus 6, minus 3, 0, 3, 6, infinity to the right, infinity to the left. So if we take A to be 3M and we take B to be 3N, right? So in H, then we say that A minus B will be 3M minus 3N, which is 3 into M minus N. So you can see this 3M minus N now, which will still be in H, because whatever you like, whatever M minus N is, whatever at all. As far as um you know as far as M and N are in H, so M and N are also multiples of of uh of 3, right? So as far as M minus N are in H, so 3 into M minus N is also in H. So we can say 3Z is a subgroup of Z uh, under addition. So 3Z is a subgroup of Z under addition. That's what this has shown us. Of course, we're still going to talk about subgroups deeply later, so not to worry. So cyclic groups and generators now. So a group G is cyclic if there exists a particular G belonging to the big G, a small G belonging to big G, such that every element of G is generated by G. So you're going to learn the idea of generation very soon. So in additive notation now, we say that this G, right angle, left angle, G, right angle, is equal to KG, where K is an integer, right? So in multiplicative notation, we say that um, so this is additive notation and we have kg like that, but in multiplicative notation we have g raised to power k. So for here it's k times g, for here it's g raised to power k, where we have k belonging to the set of all integers. So imagine this example like this. We have, imagine that we have 2 in Z8, 2 in Z8. So under addition, right? That would just be 2 times all the possible all the possible numbers. But don't forget also, okay, I'll just explain it, then I'll go over to the worksheet and explain better. So 2 in Z8 now. So we're saying that here that G, so the G that is the generator, uh the element in G that is generated by G now, and we have the rules like for addition, it's just multiples of that G. So we have 2 here now in Z8. So in Z8 addition, we already know for addition, we just have KG, with K being numbers in this, but it must still obey the rule of the set you are putting it in. So Z8, of course, you already know Z8 is 0, 1, 2, 3, 4, 5, 6, 7. All right. So in Z8 under addition now, we know 2 can only be, so since it's under addition, so it can be 2 times 0, 2 times 1, 2 times 2, 2 times 3. 2 times 4 is 8. So 8 will not fit in here because the biggest number in Z8 should be 7, right? So, okay, I mean, that has even been explained there. 0 times 2 is 0, 1 times 2 is 2, 2 times 2 is 4, 3 times 2 is 6, 4 times 2 is 8. So, since we are working in Z8, so mod 8, we take it back to 0. So, every other thing you do is going to, every other thing is going to fall within here. So, but if you have 1 now, so Z8, so you see that for 1, that would totally be Z8. So, 1 is a generator of Z8, like that. Okay, 1 is a generator of Z8. So let me go to the worksheet and explain better. If that is not clear enough, so let me try to do it again. So talking about subgroups now, we are trying to say that, we are talking about cyclic groups and generators, I mean, cyclic groups and generators. So we're saying that a group G is cyclic if there exists a particular G, all right, uh, belonging to the big G, such that every element of big G is generated by small g. So for addition, we say that G, is simply k times g, where k is an integer, basically. And then for multiplication, we say that g is the subset of all g raised to power k, such that k is also, okay, this is such that, right? Such that k is also an integer. So, and then we have this example now, you have example, you want to check for um if that g is 2 now, if g is 2, in Z8. So first of all, you need to understand the idea of Z8 is all integers less than 8. That's what it means. Starting from 0, that is. So you have 0, 1, 2, 3, 4, 5, 6, 7. No 8 because it stops at n minus 1. Okay? So with that in place, we then know that these two now, under addition, will simply be uh, all the kgs. So you have 2g, so that will be okay. I mean, don't forget the kgs now. So our g is 2, okay? But our k's now are all these ones. So our k are 0, 1, and all this. So you have 2 times 0, 2 times 1, 2 times 2. Well, 2 times 3 is also okay. But then 2 times 4 will be 8 already. But 2 times 4, so if you have 2 times 4 here, that's 8, which won't work. So this has to go because now this is 2 times 0, 0, 2 times 1, 2, 2 times 2, 4, 2 times 3 is 6. 2 times 4 is 8. But in mod 8, we have 8 divided by 8, 1 remainder 0. So it takes it back here. So if you like, 2 times 5 is 10, right? 2 times 5 is 10. So 8 in 10 is 1 remainder 2. 2 times 5 brings us back here. 2 times 6 is 12. 8 in 12, 1 remainder 4 brings us back here. 2 times 2 times 6 is 12, right? I mean, 2 times 7 is 14. 8 divided by 14 divided by 8 is 1, remainder 6. And then, so anything you do, it keeps bringing you back here. All right. So we have that. So, um, but we know that, you see, if you do for 1, right? 1 will simply be, you can do everything. 1 times 0, 1 times 0, right? 1 times 0, 1 times 1, 1 times 2, 1 times 3, 1 times 4, okay? 1 times 5, 1 times 5, 1 times 6, 1 times 6, right? And 1 times 7. We can't do 1 times 8 because 1 times 8 will take us back to 0. So here now we know this is just 0, 1, 2, 3, 4, 5, 6, and 7. So simply we see that for 1, this is simply the same thing as the Z8 we are coming from. Okay, so that is why 1 is Z8. So we can now say 1. So so 1 is a generator. It generates everything. 1 is a generator of Z8. But 2 doesn't generate everything in Z8. So 1 is a generator of Z8, like that. I mean, we'll talk about cyclic groups in more depth later. So let's talk about permutations and the symmetric group Sn. So a permutation of 1, 2, up to n is a bijection from the set to itself. So a bijection of a set to itself. So we'll learn about bijection and everything as we move on. Then all permutations form a group Sn under function composition. So in general, Sn is not abelian, meaning that it is not commutative, right? So a permutation of 1 to 1, 2 up to n is a bijection from the set to itself. So all permutations from a group Sn under function composition in general, Sn is not abelian. So let's look at this example now. So imagine you want to compose permutations here. So let sigma be 1 to 3, meaning 1 to 2, 2 to 3, and 3 to 1 again, right? And then tau is 1 to, so meaning 1 to 2, all right, meaning 1 to 2. And 1 to 2 seem automatically, so 1 to 2 and 2 to 1 basically for this one now. And then it also means from 3 to 3 because you can move from 1 to 2. If you can move from 1 to 2, it means you can move from 2 to 3, and then so you can go from 3 to 1 and 1 to 2, and so it can just run around again. So if you compute, so tau is 1, 2, right? So we have 1 to 2 or 2 back to 1. So you see here, this is 1 to 2, 2 to 3, and then 3 to 1, like this. But here you have 1, 2, meaning 1 goes to 2 and 2 can come back. So this 3 going to 3, I don't think this is necessary. So let's see, compute sigma by tau by applying tau first. So if you apply tau first, right, for tau you have 1 to 2, 2 to 3. So 1 goes to 3. So we know 1 goes to 2, right? Okay, this is one set on its own. and this is another set. So we're talking about compose permutations now. So you have one going to two and two going to three. So one goes to three finally. Then on the other hand, you have two. Two can also go back to one. So two goes to one, and then one goes to two. That means you can move from two to two. Then on the other hand, now you have three going to three, uh, three goes to three, and then one, three goes to three, and three goes back to one. So it means three goes to one ultimately. So overall, now we have sigma composed with tau is 1, 3. Sigma composed with tau is ultimately 1, 3. So looking at this whole thing together, right? Um, so here we are doing by applying tau first, right? So tau 1 to 2. So from 2 we can move to 3 now. So again here, 2 can move to 1. So 2 to 1, and then 2 to 1, and up here 1 can move to 2. Okay, so if one moves to 2, so that means we move to 2 to 2. Then all applying tau first, we have 3 to 3, and then here 3 can go to 1. So that's actually 3 to 1. Okay, so that's about composed permutation. So we have 1, 3 in that case. Now, homomorphisms. So if that is not clear enough, not to worry, we're going to talk about permutations and symmetric group as we move on. So let's talk about homomorphisms. A group of homomorphism phi, a group homomorphism 5 mapping G to H preserves the operation that phi of AB is phi of A multiplied by phi of B for all A and B belonging to G, right? So we define the kernel. The kernel of phi is all G belonging to G such that phi of G is E sub H. And we have the image of of phi is phi of G such that G belongs to G. So imagine this example. So mod map as homomorphism. So define phi such that it's z is integers with addition mapped to zn under addition by phi of k equals k mod n, right? So imagine phi of a plus b will now be a plus b mod n. That means you have a mod n plus b mod n, and a mod n is phi of a plus b mod n, which is phi of b, based on the definition we have from the beginning. Okay, because we know phi of k is k mod n. So it means that if you have a mod n, that will simply be phi of a, just like b mod n is phi of b. So phi is a homomorphism. So and its kernel is kernel of phi based on the definition we know. So we now have k belonging to the set of all integers, because our big G here is z, and that is such that k is similar to 0 mod n, and all of that will now be n multiplied by z. So like that. So I mean, there'll be more clear, more light about this as we go on later. So let's talk about rings. So here now we are just giving an overview of all the algebraic structures that we already talked about from the beginning. That all abstract algebra we know is about it's about algebraic structures. It's about structures like groups, rings, and fields. So we are going over all of these things, starting from sets, because set is the basis of all of these things we've been talking about. So talking about rings now, we've talked about the fact that a group has a set and a binary operation, and then it obeys the laws of closure, associativity. It has an identity element, it has an identity inverse. So, and that makes it a group. But for a ring now, a ring is an extended kind of group. So a ring R with two binary operations, R, you have with plus and dot, has two operations such that R comma plus is an abelian group. So the additional the under addition, it is an abelian group. Then under multiplication, it is associative, and it obeys distributive laws like A distributes over B plus C, so that we have A times B. We have AB plus AC, and A plus BC is the same thing as AC plus BC, like that. So some rings have a multiplicative identity 1. Some rings have a multiplicative identity 1, like that. Okay, that's about rings. So let's take an example of this now. So a non-commutative ring for matrices, for instance, we know multiplication under, in, under, for matrices are not
are not commutative, right? So a non-commutative ring, talking about matrices, the set of all 2 by 2 real matrices M2R form a ring under addition and multiplication. So it is usually non-commutative. Imagine you have example A 1101 and B 1011. So if you try to do AB, you get 2111 and BA 1112. Since AB is not equal to BA, so multiplication is not commutative in this case now. So I mean, in case you're wondering what's going on, I mean, I have a whole playlist on matrices where I teach different things under matrix, but let me go ahead and explain what has happened there. So you have matrix A 1101 and matrix B 1011. So AB now, AB means you're multiplying 1101 by 1011. So, and the easy way to do this is forget about this part first and focus on this. So because you have, then look at how many rows you have. That's 2 rows. So because you have 2 rows there, you're going to write this one twice. So you have 1 1 1 1. Then you also write this one twice. 0 1 0 1. Then apart from that now, you now so this one will you invert it over the first row. That's 1 1 like this, 1 1. Then this other one, okay, this other one you invert over the second row. So you have 0 1 0 1. So all you just need to do now is tidy all of this up. So you get AB. So AB now is equal to 1 times 1, 1, 1 times 1, 1, 1 plus 1. This is why this is 2. Then 0 times 1 is 0, 1 times 1 is 1 here. This is also 1, this is 1. So that's why you have AB to be 2 1 1. On the other hand, imagine you now need BA. So BA now is 1011 multiplied by 1101 like this. So again, before you what you do is leave this one alone and focus on this first. So to focus on that, right? You now check the number of rows here. So you have 1 2 rows. So that means you write each of this one twice. Each of these twice. That means you have 1010 and then you have 1111. So like this, and then you now invert this one 10 invert on the first row. That's 1010. Then this 1 1 invert on the second row. That's 1111. So then you have BA to be equal to 1 times 1, 0 times 0, that's 1 here. 1 times 1 plus 0, that's 1. The 1 times 1, 1. 1 times 0, 0. So 1 times 1, 1. There. So this is 2. So you can see now that AB is 2 1 1 1 1, whereas this is 1 1 2 1. So you see that AB is not equal to BA. And that is why we conclude that since AB is not equal to BA, you see that multiplication is not commutative. Multiplication, all right, is not commutative. It's not commutative like this. All right. So that takes us to okay, we are almost at the end of it. Oh, we still have a few things, but it's okay. I'll just it's this is a long video, but I think it's fine. Introducing us to the whole, giving us a helicopter view of what abstract algebra is about. So imagine this now. A field is a commutative ring with 1 not equal to 0, such that every non-zero element has a multiplicative inverse. So every non-zero element has a multiplicative inverse. That's what a field is with 1 not 0. So examples are all sets of rational numbers, all sets of real numbers, all sets of complex numbers. These are all fields. But if you have ZP is a field exactly when P is prime. So if you have prime, then you can say Z. So in that case, it's a field. So let's see why Z8 is not a field, right? You know, Z8 contains numbers from integers from 0 to 7, a step short of 8, right? So in Z8, we have 0, 1, 2, 3, 4, 5, 6, 7, right? So you see 2 times 4 is 0, mod 8. So even though 2 is not equal to 0 and 4 is not equal to 0, we still get 0 here. So in this case, we see that Z8 has 0 divisors, meaning not every non-zero element can have a multiplicative inverse. Therefore, Z8 is not a field, right? So that's the kind of deal we have in this case. So we are going to talk about fields generally when we get there. So quick toolkit. Now, how do we test structures? So to check if G is a group, what do? Confirm closure, confirm associativity, often known from context. I mean, you can for addition and multiplication, we can easily take it for granted that operations under for all integers or whatever you pick under addition and multiplication, they are usually there's associativity.
Find an identity element. Of course, we know how to do that. What will you add to a number or add a number to that will always give you the number that's the identity element. Then show every element as an inverse. So what will you add to a particular element? Or I mean, what will you operate with it? I think that's a better word. Not add. It doesn't have to be addition. What can you operate with a particular element, or operate the element with that will give you the identity element? That is what you call the inverse. And we established that under addition, that the identity element under addition is zero, and the inverse is negative of the opposite sign of whatever the original element is. For multiplication, the identity is 1, and the inverse is reciprocal of whatever element you're dealing with. So to show something is not a group, we only need one failure. So once one thing fails, whether it's not, if once you can see that, oh, there's no closure, or if there's closure, there's no identity. If there, or you have everything, no closure, it fails. You have everything, no identity, it fails. If you have everything, no inverse, it fails. You have everything, not associative, it also fails. So once one thing breaks down, forget it means this. The what you have is not a group. Okay, so imagine this now. We have a weird operation that still forms a group. So let G be equal to Z. That's the set of all integers, and define A star B to be A plus B plus 1. So identity E satisfies that A star E equals A, and A plus, so, and you see A plus 1 equals 1 is equal to A. So you see A plus 1 equals 1 now. A plus E plus 1 is equal to A. So in this case now, the identity is minus 1. Okay, that's one thing. So inverse of A is X, such that A times X is equal to E. And you see A plus X plus 1 is equal to minus 1. So we see that X is equal to minus A minus 2, like this. So associativity also holds. So associativity holds because A star B star C is A plus B plus 1 plus C plus 1, whereas A plus, which is equal to A plus B plus C plus 2, and A star B star C is A plus, so for B star C, you have B plus C plus 1 again. So you now have A plus B plus C plus 2. So you now see that, so Z, the set of integers with the operation star is a group, even though the operation looks unusual. So this is an unusual operation. So integer is still, it still forms a group under for this operation A plus B, A star B equals A plus B plus 1, like that. Okay. So these are some practice questions. This is a long video already, so I'll just flash them on the screen. You want to try your hands on them, going by some of the things we've done. But subsequently, we're going to, in the next two videos, I think, the next 2 or 3 videos, I'll be laying some mathematical foundation for abstract algebra. Then before we now, afterwards, then we'll start talking about group theory in earnest. So thank you so much for listening. Let me know how helpful this is for you. And if there's something else you'd like me to try, feel free to let me know. If you have subscribed already, I thank you very much. If you haven't subscribed, what are you waiting for? This is your time to subscribe. Go ahead and subscribe and hit the notification bell so you can always get alerted each time a new video is released. Having done that, you could also become a member of this channel by clicking on join, and clicking on join gives you access to bronze, silver, and gold accesses, and they come with some special privileges. All right. Ultimately, don't forget to comment, like, and share so that more people can have access to this great content I have going on here. Till I come your way again, keep doing maths right. Bye.